Hello, everyone. This presentation is going to cover electrical circuits and Ohm's law. So let's get started. Okay, so first we're going to have to define what an electrical circuit is. Um, the basic definition of an electrical circuit is a complete path for electricity to flow, meaning that it starts at point A and ends at point B. Now, point A is your positive terminal on the battery. Point B is the negative terminal on the battery. Okay, so our battery is the starting point. It's also the ending point, but depends on which post. So I know everyone's probably familiar with a normal battery. If you look at a AA battery, you look at a 9-volt battery. In this case, if we look at a car battery, there's gonna be two posts sticking up or two holes where we can screw some bolts inside of them. Okay, those are the connections where that's our starting point and our ending point. Okay, so our starting point is the red side, the positive side. The end point is the negative side or the black side. Okay, and that goes for all batteries. In order for a circuit to work, the electricity has to flow out of the positive terminal of the battery through the entire circuit. So that includes the wiring, the switch, the fuse, the resistor, such as a light bulb or a motor or something. And then it has to go back to the battery to the ground side on the opposite side. Okay. Electricity has to flow out of the positive, through the circuit, through the resistor, through the wiring, and back to the negative of the battery, the negative battery post. If it doesn't get back to the negative, it doesn't work. If it doesn't come from the positive, it doesn't work. If anywhere inside of that circuit there's a break between somehow, whether it's the bulb or the fuse or the switch or something is off or not connected, the circuit doesn't work. Okay. So the basic definition, a path for electrons to flow from positive to negative. Okay, I added a little bit more than what it says here, but again, we're trying to get into a little bit more detail at this point. So the things that we need for an electrical circuit to work are as follows: power source protection, power path, electrical load, return path, which is the ground, and circuits and controls. So switches and controls, excuse me. Now, this picture here that we're looking at over here to the right, okay, this picture here, it has everything except one thing in this list. Now, if we look at the picture closely, we have the battery right in the middle. We have a positive, we have a negative. We have a starting point, we have a finishing point. Okay, that's good. We go through the fuse, which is our protection device, which protects the entire circuit. Because of the fuse blows, that stops the electricity from flowing to the rest of the circuit, which would, in effect, protect, say, the light bulb and the rest of the wiring beyond the light bulb. It won't protect the wiring between the start and between the fuse, which is fine, but it will protect everything else after the fuse. Okay. So we have our starting point, we have our fuse, then we have the bulb, which in this case over here is the electrical load. Then we have the path that flows all the way back and around to the finishing point, which is our negative terminal on the battery. Now that is our ground circuit, ground side. Okay. So everything listed here, we have a power source, we have protection, we have power path, we have a ground, a return to path, and we have electrical load. The one thing that we are missing in this picture is the switch. So if we were to wire this circuit up as is, as we see it, into a battery, that the light bulb would work and everything would come on, but the problem is we wouldn't have a way to turn it off. We would have to unplug it, and that's not how we turn off circuits. We use a switch to to turn off circuits. Okay, so those are the things that you need. So power source protection, power path, electrical load, return path or ground, and then a switch. Okay. So as we continue on here, the one thing that we do want to make sure that we understand is placement of the fuse. So the fuse here is always before the electrical load. If we put the fuse after the electrical load, we would not protect the electrical load. So in this case, we're just looking at a basic light bulb, but a light bulb or a headlight, if you have a HID headlight, that light bulb could cost you $100, $150, $200 to replace. Okay, depends on the vehicle, obviously. An LED assembly on the newer cars, say like on a newer Mercedes or BMW, the headlights are LEDs. You replace the entire headlight. You don't replace the individual bulbs anymore. And that entire headlight could cost over $1,000 easily. Okay. So we want the protection device to be before the electrical load. It is always the very first thing from the battery. So we have our battery source where the start is, where the positive is, comes out, a wire or something is going to connect to the fuse. Then we install the rest of the circuit. Okay, so battery, then fuse, then we can put a switch or we can put the electrical load and then a switch. So then that's where we have options to place things in different ways. But the fuse has to be the first thing out of the battery. Okay. Now, on all of our cars here, everyone's car, we have what's called grounds throughout the entire car. Okay, the ground is a way to get back to the negative battery post. That's what the term ground means. So we can send a wire directly all the way back to the battery post if we wanted to, the negative post. However, it's going to cost us a lot of wiring. So let's just say your batteries are located in the front of your vehicle, and the taillight bulbs are in the back. Obviously, that's where they're taillight bulbs. If we want to wire up some taillight bulbs or some brake light bulbs, we need battery power. Okay, so we have a wire coming from the battery into a fuse, into a switch, and so on. But it makes it all the way back to the back of the car. Okay, so the battery's in the front, bulbs in the back. We have a wire that goes all the way to the back, so the whole length of the vehicle. Okay, now we could wire that bulb all the way back to the front of the vehicle to touch the negative battery post. We could do that, but it would cost a lot of wiring. So what we instead of doing that, the other better option is to take the negative post on the battery cable and bolt it directly to the metal body, to the steel body, or to the engine block or cylinder head, part of the engine or part of the chassis. Okay, by doing this, because the whole chassis is metal, it's made of steel, and then the engine block is usually made of aluminum or iron, and all of those materials are conductors of electricity. What we do is, in effect, we create a gigantic ground. So the entire body of the vehicle and the entire engine is a ground. Okay, so we can wire any electrical circuit back to those things, but back to one of those two items, either the engine block or the body, as long as there's not paint involved. So the body has to be bare metal. You have to take away the paint, and then you could bolt it to, and then bolt it to the body, and then that's your ground. So that's what we do here. That's what this picture is showing here. So instead of this light bulb going all the way back to the battery post itself, to the negative post, we just bolt it directly to ground, directly to the chassis or the engine block, because the entire engine block is the ground, because it's all made of metal. Okay. And on the, which we'll learn in a later module, the ground side of the circuit has the least amount of voltage. There's very, very little voltage. There's still a little bit, but it's usually 0.0 something, 0.01, 0.02, which is minuscule for us, comparatively. So if we continue here, so on these, anything that you see highlighted, make sure you write it down, take note of it, okay? Because more than likely it's gonna be on the quiz. So here, an electrical switch. We can install the electrical switch on either side of the load, the electrical load. That's what this is talking about. So this picture we have here, the electrical switch is installed on the power side. So the power side is where the power comes out of the battery, and before it hits the electrical load, we have a switch. Okay, so that's the power side of the circuit. The ground side of the circuit is on the other side of the electrical load. So in this case, it's a light bulb in this picture. If we were to put the switch on the other side, on the ground side of the bulb, the circuit would still work fine, still operate properly, and everything would be fine. But it's just the placement of the switch. We can do it before the electrical load or after the electrical load, and we'll get the same result as far as the circuit working. Most cars are wired to where the switch is actually on the ground side of the circuit, meaning after the electrical load. Okay. Now, there are four types of electrical faults. Now, I would recommend, highly recommend that you guys write these down, that everyone remembers them and knows them, okay? Because this is the basics of electrical fault circuit, diagnosis. Um, these four are very common, and these are really the only four that can happen in electrical. The thing that throws a little wrench in the system nowadays are computers, computer software. Software is another issue that can mirror or make us think there's an electrical problem, but in reality, it's just a software issue. Okay. So that's why whenever cars come in nowadays, the first thing we do is we just update the software to make sure that all the software is good to go. Then we can diagnose electrical problems. Okay. So the first one is open circuits. So an open circuit, very, very simple to understand. Okay. Open circuit just means that the electricity does not get to ground. It goes out of the positive into the circuit. It never gets back to the ground portion of it. Okay. That could be, so example of an open circuit is a broken wire, a blown fuse. When you turn the circuit off, it's an open circuit. You create an open circuit by turning it off. Okay. By turning a light switch on, off, you create an open circuit. Okay. So those are pretty simple to understand. The symptom, meaning a customer would come in and say, my light bulbs don't work, my car won't start. You know, the thing that they're trying to turn on or make start or make work doesn't work. That's the symptom of an open circuit. Okay. So next one, short to ground. Short to ground acts exactly like an open circuit. So a short to ground can be an open circuit. However, the one thing about short to grounds that you have to check all times is the fuse. If the fuse is blown, that indicates a short to ground. In a traditional open circuit, the fuse may not be blown. Okay. So the symptoms are exactly the same. The circuit won't work. This customer turns on their headlights or whatever it is, or steps on the brake lights don't work. That the symptoms are the same, meaning it doesn't work, but the fuse is what's going to determine, are we looking for an open or are we looking for a short to ground? If the fuse is blown, we're looking for a short to ground. If it's not blown, we're looking for an open circuit. Okay. Now the next one, short to voltage. Short to voltage is the most complicated one out of the four. It's the one that where we have two wires touching together that are both power wires. Okay, so meaning that wires can rub together inside of a conduit inside of the car. As you know, as the car moves and you open the doors and close the doors and trunk and hit hood and all that, the wires inside move and they could start rubbing together and start touching. Now, if a power wire touches another wire, that's when we have a short to voltage. Now, the symptom of short to voltage is things turn on and off by themselves. I turn one switch on and another thing turns on. Like if you have two reading lights, which are above the mirror, you turn one on and the other one turns on itself. Um, or a really, really weird one would be like you turn on the windshield wipers and the headlights turn on. So that would indicate a short to ground. So the fuse is not blown, but weird things are happening. You know, customers may say like my car is possessed. That would be like a symptom of a short to ground. Okay, and those are hard to find. They're very difficult to find. Luckily, they don't happen that often, but when they do, they're very frustrating. Then the last one we have is high resistance. So high resistance, the fuse is not blown. It's good. The circuit works, but it doesn't work very well, meaning the window motor is slow. It works, but it doesn't work well. The car starts, but it takes a long time. It's really, really slow, and eventually it starts. So those are symptoms of high resistance. And what can cause high resistance are what's listed there: a loose connection, a bad connection, or just weak electrical connection. So we're dealing more with a connection issue or a burned up motor or a very old component, something like that. Okay. So those are the four basic electrical faults that we can have. Now we'll go over them a little bit individually, just give you some examples. So this is for an open circuit. So obviously a broken wire, blown fuse. You know, why did the fuse blow? That's another story, and that's where we're going to come into play. We're going to try and find out, is it an open or is it a short to ground? Okay. Did the fuse blow because we had high amperage, which would indicate a short circuit, or did the fuse blow because some other, someone was messing around with and did touch something they weren't supposed to, that created the open? So that's something we have to find out. Okay, but open circuit, no current will flow. I think that's one of the main things. So we're going to have no amperage going through the circuit. Okay. One of the definitions that we need to understand too is the word continuity. So continuity refers to a complete path for electricity to flow. So continuity is good. We want circuits to have continuity. If they don't have continuity, they will not work. We have to use a ohm meter, meaning we're going to check resistance on a circuit. So we can check resistance on anything. We can check it on a wire, on a fuse, in this case, in this picture. We can check it on a motor. We can check it on, almost anything. And if it has resistance, it will give us a number on the face of the meter. and that means it has continuity. So we can get a wire and check it, and that just tells us that that wire is complete, that there's no breaks in between. The reason we do that is because even though, yeah, it looks okay, we got to check it first. Okay. You can pull out a wire or wiring loom out of a car and it may look okay, but the thing is, how do we know it's okay? Because the wires are inside of the insulation. You don't actually see the metal bare copper wire. What you see is the insulation around it. So this is a way for us to check if everything works. Okay, so the word continuity, complete and continuous through electrical loads. It comes back to ground. Okay. Excuse me, sorry. And okay, for the next one, we do have another option besides fuses, which are called circuit breakers, and those can be used. They're not used very often. A circuit breaker is usually used in a house. Older cars may have had circuit breakers at one point, but all newer cars use fuses. But if you ever heard the word circuit breaker, it means the same thing as a fuse. Okay, a circuit breaker can blow, meaning it'll pop. Once you have too much amperage, it pops open. It creates an open circuit, and then you can either manually go back and close it manually, or over time, when it cools down, it'll close by itself. Okay. Now let's look at a short to ground picture. Okay, so we have a short to ground picture here. Okay, and sorry, and we have a basic circuit. The thing that we want to point out is the fuse is blown. Okay, so short to ground will cause the fuse to blow. It'll create an open circuit. The customer will say that the circuit doesn't work, the switch doesn't work, the item doesn't work. We have a blown fuse, but look what happens to electricity where it goes. Now, all electricity, in order for the circuit to work properly, has to go through an electrical load. In this case, we have a light bulb over here that where it's supposed to go, but it doesn't. Instead, what it does is it goes from positive through the fuse, through the switch, and straight to ground. It never gets to the electrical load. If this was to happen into a circuit, the amperage would skyrocket and the fuse would blow. Okay. So again, we're always checking for blown fuses first to determine, if the fuse is blown, okay, we may have a short to ground. All right. If the fuse is good, we may just have an open circuit or possibly a short to voltage, which is this picture here. So we look at this picture here. Our fuse is good. Our ground is good. Our battery is okay. We have electricity flowing out of the battery through the fuse and into our first junction. However, because there is a short to voltage on the other side of the switches, when we turn one switch on, both lights come on, both bulbs come on. Okay. If we were to turn the bottom switch off and the top switch on, the exact same thing would happen. So the switches are not working independently as designed. What happens is these wires that are in between, they start to melt together and they start to touch each other. So the copper to copper starts to touch. If we have copper to copper touching, when we refer to copper, we usually refer to a power wire. That this is when we can have a short to voltage. Okay, if we go back, I'm gonna go back real quick. If we go back here, when we have wires that touch the steel body or some sort of metal, that's when we have a short to ground. Okay. So again, on the short to voltage, these one switch controls both, and that should not happen. They should work independently of each other. Okay, and this is just a quick review. So when we have a short to ground, we're assuming that some sort of wires may be touching the steel body or touching another ground wire. And then when we have a short to voltage, we're looking for and assuming that we have a copper to copper touching problem, meaning the wires have melted within the insulation and they're touching each other. Two power wires may be touching, or a power and a ground wire may be touching. Okay, so that's what we're looking for on those two types of circuits. Types of faults. Now we have the last one, which is high resistance. So high resistance, again, symptoms, dim lights, slow motor. So the circuit works, it just doesn't work well. It doesn't work as designed. It works slow. So the lights could be low. Instead of having bright headlights, you have dim headlights. Instead of the motor, your window motor going up really fast, it goes up and down really, really slow. Those are all examples of high resistance. Okay, the circuit works, it just doesn't work very well. Current still goes through. Maybe not enough current. We'll have higher resistance inside the circuit if we were to measure it. But we can measure amperage and see that we have low current and things are just working slow. These are a little bit easier to understand, easier to find because we're looking for loose connections. We're looking for motors that are burned up. We're looking for, burned terminals. Something like that is what we'd be looking for in this instance. Okay, on this one, so I'm going to skip this one. I might come back to it. But again, if definitely look at this picture, read what it says on top, and try to understand what's going on here because we're going to talk about Ohm's law right now. Now we're going to go back to amperage, voltage, and resistance just real quick because we're going to be using these things in a math equation. Ohm's law is a basic math equation. Ohm's law tells us that it's going to take 1 volt to push 1 amp through 1 ohm. Okay. And I'm going to show you guys the picture of the equation right here. So E equals voltage, I equals amperage, and R equals resistance. Okay. So E short for electromotive force, which is voltage. So that's why we use the letter E. I is short for intensity. And that's why we use I for amperage. And then R is for resistance or ohms, which stays the same. Okay. So that's where we get the E and the I from for electromotive force, which is voltage, and intensity, which is amperage. All right. So the equations down at the bottom is what we're going to have to look at. So we're always going to be given two, or one of them. Yeah, sorry. We're always going to be given two of them. So we're going to be given, say, voltage and resistance, and we got to find amperage. Or we're going to be given amperage and resistance, and we got to find voltage. Okay. So down here at the bottom, you'll see the three equations. So make sure you write those down and keep those in mind as we move forward. You will be using these throughout the entire class too. So please do not forget these. Please look at them, remember them, and understand them. Now, Ohm's law. Here's the equations just written in a different way. Maybe this is a better way for you to understand them. Write them down however you feel is best for you to understand them. Okay. But this is only, if you look at it, it's only a basic multiplication and basic division problems. That's it. We have 2 division problems and we have 1 multiplication problem. Okay. So E is volts, I is amperage, and R is resistance. Now, in order for us to find numbers and find out how much voltage or resistance or amperage we have or need in a circuit, we have to know at least 2 of them. Okay. The one that's always common for most cars is going to be the voltage. The voltage is 12 volts, right? If we want to be very, very exact, it is 12.6. But voltage is the most common one, so that's easy. We usually know what the voltage is to start with, 12, right? If not, we can measure it and find out. The resistance is the other easier one to find because we can get the electrical load that we're trying to put into a circuit. In this instance here, this picture we're looking at, it's a bulb. So we can measure that the bulb is 4 ohms in this instance. Okay. So we have a 4 ohm bulb and we have 12 volts. So how many amps is going to go through the circuit if we have those two numbers? So if we go back one, we have 12 volts and we have 4 ohms. So 12 divided by 4 will give us 3. It's that simple. Okay. So 12 divided by 4 will give us 3. 12 volts divided by 4 ohms gives us 3 amps. So that way we would know roughly that 3 amps is going to flow through the circuit. So that way we know the fuse that we have to put in there has to be roughly 4 to 5 amps. Okay, they really don't make 4 amp fuses, so we have to put a 5 amp fuse. Okay, and that's kind of like if you're going to install, say, headlights or running lights or fog lights on your car. This is how we can figure out how big of a fuse you need to put in there, and also what gauge of wiring you need to put in there. Okay. Wiring is another module, and we'll get to that eventually. Now, how these 3 things interact with each other. If voltage goes up, amperage goes up with it. Okay. The ones that are highlighted are the main ones that happen in reality. You can look at the whole chart, and I encourage you to, but these two, so row number 2 and row number 4 are really the main ones that we're going to understand that really happen the most. So if we have a voltage spike in a car, we have to understand that the amperage can go up with it. So voltage and amperage move together. If voltage goes up, amperage goes up. If amperage goes down, voltage goes down. Okay. Now the other one is resistance and amperage. They do the exact opposite of each other. So voltage traditionally, as long as everything is working fine, as long as your battery is good, your alternator is good, the voltage should stay roughly the same all the time. It shouldn't be going up and down. Okay. The only time it goes up and down is if there's something wrong with your car, if there's something wrong with your battery, wrong with your alternator or wiring. But for the most part, our cars are pretty good and everything should work good. So if the car's off, we should have 12.6. If the car's on, we should have roughly say 13.5 to 15 volts. And the voltage should not be fluctuating that much. So what happens is the resistance and the amperage, those are the things that be going opposite of each other. So if our resistance goes up, our amperage goes down. If our amperage goes up, our resistance goes down. Okay. And so they do the opposite. Voltage and amperage go up and down together. Resistance and amperage do the opposite of each other. Okay. So those are the main things we want to take away from this. And the very, very last one, we're just going to talk about Watt's law really, really quick. Now, Watt's law is found more so in electric vehicles. So if you take AUTO-260, we'll talk about Watt's law much more in that class. Okay. Now, Watt's law is here to determine power. So let's say we have an electric motor and we have a size of a battery. We have a 12-volt battery. We have an electric motor that produces 1,000 watts. A battery that's 12 volts. How many amps is that going to produce? So we can find that out pretty quickly. I'm going to show you the formula right now. It's going to look exactly like the Ohm's law formula, okay, which it almost does. So we use the I for amps. We use the E for volts, which is still the same. The thing that we don't use in Watt's law is resistance. Okay, we don't use that here. What we use instead is the P. So notice the P is on the top position. And then we have our I and our E at the lower positions next to each other. Okay, so P stands for power, also known as watts. So watts is think of watts as horsepower is to mechanical power. So a gasoline engine is measured in horsepower. An electric motor is measured in watts. So how much power does the electric motor produce? Okay. All electric motors have a power rating. I mean, things like your microwave at home has a power rating. How many watts does your microwave at home produce? Some produce like 500, 600, some produce 1,000, some produce 1,200. Okay. An electric vehicle can produce hundreds of thousands of watts. And that's how we can translate that into horsepower by dividing that by 746. Okay. So if electric motor produces 300,000 watts, you take that number, you divide it by 746, and that'll give you how much horsepower that electric motor makes is the equivalent. Okay. So in this case here, let's look at these two examples over here on the right. We have volts at 12, amps at 1. Now, amps and volts are next to each other. So when two letters are next to each other in math, that tells us that we got to multiply. So we would take 12.12. Okay. I'm going to do this in my calculator here on the side. 12 times 1.2. It's going to give us 14.4. Okay. So if we had 12 volts and we had a 1.2 amps circuit, the motor at the most would produce 14.4 watts. Okay. We go to the bottom here, the bottom one, that one's a little easier. That's 10 times 150. Okay. 10 volts times 150 amps will give us 1,500 watts. So it's a 1,500 watt motor or microwave or whatever you want to look at. Okay. That's how we figure out watts. Very, very similar to Ohm's law. All right. So I hope you enjoyed this lecture. And again, if you always have any questions, please feel free to reach out to me at any time. Okay. Thank you very much.